Hi, and welcome to Calc Apps Day 3. Today we are talking about motion. Our understanding goal is motion in a straight line and its relationship to displacement, velocity, and acceleration. Displacement is another word for position. Motion in a straight line. Suppose an object P moves along a straight line so that its position S from the origin O is given as some function of time t. We would write S equals S of t, where t is greater than or equal to 0. S of t is a displacement function, and for any value of t, it gives the displacement from O. S of t is a vector quantity. Its magnitude is the distance from O, and its sign indicates the direction from O. So it is clear that if S of t is greater than 0, P is located to the right of O. If S of t is equal to 0, then P is located at O, and if S of t is less than 0, then P is located to the left of O. So a motion graph. Consider S of t to be equal to t squared plus 2t minus 3 centimeters. S of 0 is -3, S of 1 is 0, S of 2 is 5, S of 3 is 15, and S of 4 is 21 centimeters. So let's draw what this actually looks like on a number line. So I have 0, 5, 10, 15, 20, and 25 on my number line. When t is equal to 0, my position is at -3 centimeters. That means I'm to the left of the origin. So right about here. That's my position. And this is t equals 0. And then when t is equal to 1, I'm at 0. So this is t equals 1. When t is equal to 2, I'm at 5. When t is equal to 3, I'm at 12. When t is equal to 4, I'm at 21. So all I've done essentially is plot my position on a number line and labeled my t values. Okay, moving on to the next page. We have velocity and acceleration. The velocity, or average velocity, the key here is average, of an object moving in a straight line in the time interval from t is equal to t1 to t is equal to t2 is the ratio of the change in displacement to the time taken. Okay, again, displacement is position. If S of t is a displacement function, the average velocity, okay, the average velocity is the slope. On the graph of S of t, the average velocity is the gradient of a chord, which is just a line segment. Okay, when you see instantaneous velocity, that means take derivative. In chapter 17, we established that ds dt is equal to s prime of t, and that the instantaneous rate of change in displacement per unit of time, or the instantaneous velocity. If s of t is the displacement function of an object moving in a straight line, then v of t is equal to s prime of t, which is equal to the limit of s of t plus h minus s of t over h. And that is the instantaneous velocity, or the velocity function of the object at time t. On a graph of s of t, the instantaneous velocity is the gradient of the tangent. Remember, a gradient is slope. The average velocity. If an object moves in a straight line with a velocity function v of t, then its average acceleration on the time interval from t equals t1 to t equals t2 is the ratio of the change in velocity to the time taken. Again, average means we use the slope formula. Instantaneous acceleration. Okay, the key is instantaneous here, but acceleration is also important because that is the second derivative. Or it could be considered the derivative of velocity. That's supposed to be derivative. All right. Yesterday in class, I kind of mentioned that you have your displacement function or your position. It's not going to go there, but that's your position. And when you take the derivative of that, you get your velocity. And when you take your derivative of that, you get acceleration. Okay? So then if a particle moves in a straight line with the velocity function v of t, then the instantaneous acceleration as time is t is a of t equals v prime of t, which is the limit of v of t plus h minus v of t over h. So an example. The particle moves in a straight line with displacement from the origin given by s of t equals 3t minus t squared meters at time t seconds. Find the average velocity in the time interval from 2 to 5, and then find the average velocity of the time interval from 2 to 2 plus h, and then take the limit and comment on its significance. So A is the average velocity. So we need to find s of 5 minus s of 2 all over 5 minus 2. When we're finding the average, we use the slope formula. If I substitute into the function for 5, I would get 3 times 5, which is 15, minus 5 squared, which is 25. So 15 minus 25 is negative 10. Minus s of 2, if I put in 2, I will get 2 times 3, which is 6, minus 2 squared, which is 4, so 6 minus 4 is 2, all over 5 minus 2, so I get negative 12 over 3, which is negative 4 meters per second. And it's negative, so all that means is it's moving left. Part B, we're still finding the average velocity. So we're still using our slope formula. And for this one, we're going to use s of 2 plus h minus s of 2 all over 2 plus h minus 2. So if I put in 2 plus h everywhere there's an x, I will have 3 times 2 plus h minus 2 plus h, the quantity squared, minus s of 2, which we found in part A to be 2, and 2 plus h minus 2 is just h. So if I clean this up, I will have 6 plus 3h minus, I have to write it twice and FOIL it, or double distribution, and I will get 4 plus 4h plus h squared minus 2 all over h. So it's 6 plus 3h minus 4 plus, sorry, minus, distribute my negative, 4h minus h squared minus 2 all over h. So negative 2 and negative 4 is negative 6, and a positive 6 will all cancel out. So I'm left with 3h minus 4h minus h squared all over h. So we get negative h minus h squared over h. And I can take an h out of everything, divide by h. So we get negative 1 minus h meters per second, provided h is not equal to 0. Part C asks us to find the limit as h approaches 0 of f of 2 plus h minus s of 2 all over h. Well, we already did the math in part B, so we're going to take the limit as h approaches 0 of negative 1 minus h. And when I put in 0 for h, I will get negative 1, that'll be meters per second. And the comment on the significance is this is the instantaneous velocity of, of the particle at time t equals 2 seconds. And that is it.